In the previous video on quantum entanglement, we established that entanglement exhibits some strange properties, and in particular, that it exhibits behaviors that appear at odds with special relativity. A measurement of 1/2 or 1 part of an entangled state can collapse the superposition of the entire state, determining the behavior or the properties of a particle that can be arbitrarily far away, despite the fact that in relativity there is a limit to how quickly information can propagate through space. To analyze what's going on here and to establish why this isn't actually a problem, let's start by looking at the classical example of entanglement that we started with last time, with our red and our blue marbles hidden inside boxes given to Alice and Bob, who then go on their merry way. It's comparatively straightforward to understand why this example does not have a problem with special relativity, because even though it's true that Alice knows immediately upon seeing that her marble is red that Bob's marble is blue, her observation that her marble is red, it doesn't actually change or affect anything about the state of Bob's marble. Bob's marble was always blue and Alice's marble was always red. She can do this because Alice had some information about the system before she even opened her box. She knew that there was one red marble and there was one blue marble, and that one of the marbles was given to Bob and one was given to her. She got this information when she went to go pick up her marble, before she ever went far away from Bob. Or alternatively, maybe the marbles were delivered to Alice and Bob, and whoever delivered the marble to Alice also told her that Bob got the other marble. And so part of the information about the system was already provided to Alice and to Bob. They start out with partial information about the nature of the system, about the state of the two marbles. What they're unaware of is which marble is where. And so it is true that Alice learned something immediately about the state of something that could be really, really far away. But it doesn't actually affect anything really far away. And the reason why Alice can do this is because that information, or part of the information, was already given to her. It just wasn't enough information to know exactly what was going on. And then upon seeing that her marble is red, that fills in the blanks, and so now she no longer has any questions. Some of this is also true for our quantum mechanical system. Even though Alice and Bob only get 1/2 of our entangled state in this example, they also start out with some information about the nature of the entire state. Whether because they set it up or because whoever sent the electron and the positron from the pion's decay to them told them where the particles came from, they know that these two particles are entangled in such a way that their spin angular momenta along a particular direction always have to be opposite. Because they know that the total angular momentum has to be 0, since that's what it was before the decay. If Alice measures the spin of the electron in their agreed upon direction and finds that it was spin up, then she knows that the positron is spin down, and that when Bob measures, or perhaps already measured, the spin of his particle in the same direction, that he will find, or already found, that it was spin down. Or conversely, if Bob measures the spin of his positron and finds that it is spin down, then he knows that Alice either will or already has measured her electron and found that it was spin up. The reason why this is possible is because Alice and Bob start with the partial information about the system, that the sum of the angular momenta of these particles in any direction has to be equal to 0. And so they know that their results will be anti-correlated to each other, which is to say that they will always be opposite of each other. That's information that they started out with. Whoever was holding on to the pion and who sent the electron and positron to Alice and Bob respectively provided that information to Alice and Bob. So that's something they knew before the particles ever got to them. Whether that information was sent to them by telephone or mail or email or whatever, through some method of communication, the person who's managing the decay of this pion sent that information to Alice and Bob ahead of time. So they already were given part of the information about the system, of which they would then receive a piece of. Measuring their own piece of that system is then enough to combine with the information that they started out with to figure out what's going on with the whole system. So far, this is no different from the classical example with the marbles that we just discussed, where Alice and Bob are able to learn something about the state of something really, really far away by measuring something local to them. And they can do that because they start out with some information about the total state, which means they already have some information about what's happening really far away. And now they're supplementing it with information about what they have right in front of them, which allows them to exclude some of the possibilities, leaving, in this case, only one left. What's different, once again, though, is superposition. Because unlike with the marbles, where Alice had the red marble and just didn't know it, and Bob had the blue marble and just didn't know it, in this case, as we discussed before, neither Alice nor Bob has a particle that is spin up or that is spin down, but instead both of them have particles that are in a superposition of states. This is significant because if Alice measures the spin of the electron, she will find that it is either spin up or spin down. The superposition is collapsed. And that means Alice's measurement of the electron affects the quantum mechanical state of not just her electron, but of the entire system, including the positron with which it's entangled. So if Alice measures that the electron is spin up, then the wave function, which started as this superposition of two states, is collapsed, because if the electron is spin up, then this second term is no longer a possibility. Our wave function collapses to just this first term, and it's renormalized so that the overall probability is still equal to 1. This is fundamentally different from the example with the marbles, because the colors of the marbles were well-defined properties, and a measurement of the color of one of them doesn't change anything about the other, it just allows us to piece together the different parts of the puzzle. But here, the measurement of one part of the system is actually affecting the whole system, including the other part of it. Even though the positron could be super far away, it could be light years away, the moment Alice measured the state of the electron, the state of the positron is also determined, whether or not anybody has measured it yet. I want to emphasize that it's not particularly important that Alice is the one performing the measurement first, right? Again, as I showed the other in the previous lesson, in different reference frames, right, that might not even always be the case. So what we just discussed here, this collapse process, it could occur when Alice measures that the electron is spin up, or equivalently, if Bob were to measure the positron and determine that it was spin down, that measurement would also collapse the wave function, and it would also again select out just this first term, because if the positron is down, this first term represents the only remaining possibility. This certainly does appear to, in fact, contradict special relativity, which imposes a speed limit on how quickly effects can propagate. And like I raised in the previous video, depending on when and where Alice and Bob make their measurements on their particles, which one performed their measurement first might even be different in different reference frames. So which action caused the collapse? For now, let's set aside that second question of which happened first, and let's focus on just one reference frame in which Alice or Bob performs their measurement before the other. To keep things simple, let's say that Alice always this is like my third time trying to say this sentence. To keep things simple, let's say that Alice always performs her measurement first. Though I want to emphasize that it doesn't matter. We could make Bob do it first and it won't change anything. We could even make it so that a different one does their measurement first each time, but it just makes things messy. It doesn't actually change the result. So we're going to keep it simple, and Alice always performs her measurement first. They maybe came to an agreement that that's the way they're going to do it. As we've discussed before, in order to really quantify things in quantum mechanics, we have to consider running an experiment many, many times, since each event is probabilistic. So let's imagine that we have a large collection of pions. Each time one of them decays, we send the electron and positron to Alice and Bob respectively. They perform their measurements and so on. So now let's consider the different possible outcomes. So let's say that Alice measures the spin in the z direction of her particle. Based off of what we've learned so far, 50% of the time, Alice will find that it is spin up, and the other 50% of the time, Alice will measure that it's spin down. If Bob then performs his measurements in the z direction, then every time Alice measured spin up, Bob measures spin down. And every time Alice measures spin down, Bob measures spin up. And that means, once again, there is a 50% chance for each of those cases for Bob. You'll notice, first of all, that this is completely symmetric. So if we said that Bob performed his measurements first, this exact same little chart that we made would still apply. But moreover, the results that Bob finds are completely consistent with him measuring a state in superposition. Half of the time he performs his measurements, he finds that it's spin down, and the other half he finds that he gets spin up. So each time he gets a particle, it's as if it has an indeterminate state of spin, and when he measures it, he collapses the superposition and finds one or the other. But Alice experiences the same thing. And we set this up originally so that Alice actually performed her measurements first, and the fact that it still looks to Bob like he has indeterminate spin states is an indication that while Alice's action over here has caused an effect on the positron state, that effect is not discoverable by Bob, because Bob's results are the same as what he would expect if Alice hadn't performed her measurements. So, in other words, the expected and actual results that Bob would find are independent of whether or not Alice performed her experiment already. So while it is true that Alice's measurement of the electron collapsed the wave function for the electron-positron system, immediately, instantaneously, even for the positron which is far away, the effect of that collapse is indetectable to Bob. If that weren't the case, this would be a really big problem, because it would mean Alice and Bob could come up with a scheme. Alice could say, listen, if I perform my measurement, that means I'm sending you a 1. And if I don't measure my particle, I'm sending you a 0. And that way, if Bob could tell whether or not Alice has already performed her measurement, he could figure out whether Alice sent him a 1 or a 0, and that information would be conveyed instantaneously. And if Alice could send information instantly to Bob over great distances, this would violate special relativity. It would create problems with causality. We could create time loops, as we showed a while ago in class with our space-time diagrams, and that would be a really big problem. But because the effects of Alice's measurement are completely and fundamentally indetectable by Bob, there is no transfer of information. There is an effect, yes, but not one that is discoverable. Even though in this example we set it up so that Alice did perform her measurement first, Bob cannot tell, not even in principle. For him to figure out whether Alice measured the spin of a particular electron, for example, if Bob wants to know, I wonder if Alice measured the spin before I did on the third system that we received. The only way for him to know is for him to get on the phone with Alice and for them to communicate by classical means, if you will. If they're talking by phone, they're using electrical signals or radio waves or something, and all those things travel at or less than the speed of light. To understand how this resolves the apparent contradiction here, we have to go back and we have to think about how we demonstrated that the speed of light represented the maximum speed at which anything could move through the universe. The way that we did that was by reductio ad absurdum. We proved that if something could travel at a speed greater than c in any particular reference frame, then it would lead to time paradoxes and a loss of causality. And since our observations of our universe seem to indicate that causes do precede their effects, we would then concluded that faster than light travel or signaling isn't possible, because it would be inconsistent with our observations of a causal universe. But importantly, our base assumption in that logical proof wasn't really just that something was traveling at the speed of light. It was more specific than that. It was more stringent than that. Our assumption was that something could detectably travel faster than the speed of light. I think the example we used in class, if I remember correctly, was sending a message to your grandmother that you baked her cookies or something. And if you sent her that information faster than the speed of light, your grandmother could then receive the information that you baked her cookies, that you finished baking her cookies, before you actually started baking them, at least in some reference frames. And then to make it worse, she could then send a message back to you, uh, thanking you for making the cookies, which you would then receive before you even started making the cookies. And so now you have a loop where you made the cookies, you sent her information that you made the cookies, she sends you back a thank you note, which you received before you made the cookies, and therefore she's thanking you for something that you haven't done yet and that you haven't told her that you were even doing. The communication between you and your grandmother in that example is detectable, right? Because you're sending information, you're sending a message to your grandmother that she can then receive and decode and then act on. But what we have here in this example of entanglement is not that. Through this process, Alice can't tell Bob anything. Bob can't tell whether Alice did anything, and vice versa. So there's no transfer of information. And so the speed of light is not really the maximum speed at which effects can propagate. It is the maximum speed at which detectable effects can propagate. Now, the most concise way of defining the speed of light is really just as the invariant speed of the universe, and all of the other things kind of come from that. But it's often convenient to describe it in other ways. And so, for example, we often do describe it as the maximum speed at which things can travel. We describe it most often as the speed at which light travels through a vacuum. And because of this subtle but really important differentiation between effects that can be detected and effects that cannot be detected, the speed of light is also sometimes called the maximum speed of information. Because an effect that does not convey information doesn't violate anything about relativity, even if those effects propagate arbitrarily quickly. And just to reiterate, this is manifested in this example of entanglement as the fact that the statistics of Bob's measurement results are unaffected by Alice's measurements. On an individual case-by-case basis, Alice's measurements did have effects on Bob's state, right? The moment Alice collapsed the wave function and determined that this was spin up, Bob's is immediately determined to be spinned out. That's a real effect. However, Bob can't attribute his measurement of spin down to anything that Alice did, because Bob doesn't know whether or not Alice performed the measurement. And even though we established that Alice and Bob agreed that Alice would always measure hers first, how is Bob supposed to know Alice is telling the truth? So this kind of effect, the collapse of superposition of this entangled state, cannot be used to signal between Alice and Bob. Alice can't signal to Bob any kind of information, and Bob can't infer anything about Alice from his own measurements. And therefore, we can't reconstruct that paradox that we did with special relativity in our spacetime diagrams, where we showed that signals traveling faster than the speed of light could lead to paradoxes, because again, nothing over here can act on the effects of the measurements over here, because the effects are indistinguishable from the random noise of quantum mechanics itself. This leads to something called the principle of locality. This is actually the combination of two different ideas. One is that it means that for an action at one point to have an influence at another point, something in the space between them, such as a field or a rope or some physical object, must mediate the action. This idea is actually super old. It can be traced back to Newton and even before. When Newton formulated his theory of gravity, for example, he stated that he thought it was patently absurd to consider that the gravitation between two bodies occurred without something mediating them. He didn't know what mediated them. He didn't know whether there was some invisible but material thing through which gravity acted, or whether it was something more immaterial. And as physics developed, eventually the idea of fields came into play, which is now how we understand these forces that act at a distance, such as gravitation, such as electromagnetism, and so on. The other part of this is the consideration from special relativity that no such action or influence can be transmitted between distant points in space at a speed exceeding the speed of light, or the invariant speed. As Einstein put it, the principle of locality is essentially the opposite of what he called spooky action at a distance, which is something an effect occurring at one place, potentially affecting something far away, with nothing in between and arbitrarily quickly. Now, quantum entanglement, as we just described it, does not satisfy the principle of locality. And in fact, in this interpretation of quantum mechanics that I've been teaching you, the Copenhagen interpretation, quantum mechanics is not, in fact, a local theory. It violates this principle of locality that Einstein put forward. Einstein put forward this principle as something that he believed should be true about the universe, that this first point should be true, which physicists, by the way, still almost entirely consider to be true to this day, but also based off of this theory of special relativity, that this second point should be true as well. And the general consensus is that this second point maybe is not so true after all. I'm defining this term now because it's relevant to what we were just discussing, and also because it will be useful later when we start discussing different interpretations of quantum mechanics. It's very closely related to causality, but it is subtly different because a non-local theory can still be a causal one. Because as we discussed, if effects or actions that do not carry information travel at speeds exceeding c, they don't break causality. They can't lead to those weird loops where causes or where effects precede their causes and so on. So locality, as defined here, is actually a stronger requirement than causality. It imposes even stronger constraints on what can happen than causality itself does. Now, if you go and you start reading about locality, it can be very confusing because unfortunately, locality can mean different things and they're not always consistent with each other. The principle of locality, as I've defined it here, is called Einsteinian locality sometimes. In quantum field theory, there are other variations of locality that are very closely related to this, but they mean slightly different things. So if you start reading about this online, you might occasionally encounter things that seem to contradict this definition that I've provided you with. And that's because it's probably referring to a different definition of locality in a different context. This is what I'm going to mean by locality when I say it. Now let's go back to our example with Alice and Bob in the muon, because I want to take this example even farther. So far, we've restricted ourselves to the scenario where Alice and Bob coordinate and always measure the spin of their particles in the same orientation. So they're both measuring spin in their common z direction. But now I want to talk about what happens when they mix that up a little bit. The way that we're going to do this is that Bob is always going to measure spin in the z direction. Just for simplicity, again, it's going to generalize to all other circumstances. But we're going to say Bob always measures spin in the z direction. But Alice will sometimes measure spin in the z direction and will other times measure spin in the x direction. Now, every time Alice measures the spin of her particle in the z direction, we already established what's going to happen with Bob and so on. So we've already done half of this. But if Alice measures her particle to be spin up in the x direction, that means that the state has collapsed so that the electron is spin up in the x direction and the positron therefore has to be spin down in the x direction. Because the initial spin of the pion was 0 in every direction. That means if I add up the component of spin of the electron to the component of spin of the positron in the same direction, they always have to be opposite. So Sx of the electron and Sx of the positron will always be opposite directions. Same with Sz of each of them, same with Sy of each of them. And even if we pick some angle somewhere in between those, the same would be true of that as well. So in a particular direction, the electron and positron must have spins in the opposite orientation. So we can elaborate on this, and if Alice measures spin in the x direction and finds that it's spin down this time, that means the state of the positron must be spin up in the x direction. And whether or not Alice finds spin up or spin down in the x direction is the same as it was in the z direction. It's random completely, so it's a 50-50 chance. So if Alice measures the spin in the x direction, there's a 50% chance that she finds spin up, and there's a 50% chance that she finds spin down. Now, Bob is still only measuring spin in the z direction. But this time, if Alice performed her measurement in the x direction and collapsed the superposition, so that the positron state becomes well defined in the x direction. So if Alice measures spin in the x direction and finds that it was spin up, that means the state of the two-particle system has collapsed, and now the positron has a well-defined spin down in the x direction. That means Bob is measuring spin in the z direction of the state x minus. And we've been doing that for months now. When you do that, you have a 50-50 chance of getting up or down. So when Bob performs his spin z measurement of the particle that Alice has collapsed into the x minus state, he has a 50% chance of finding spin up and a 50% chance of finding spin down. Again, in the z direction. He's measuring it, in this case, in a different direction than Alice's. And the exact same thing is true if Alice measured that her particle is spin down in the x direction. That means Bob now has the state x plus, and he's measuring SZ, so he'll once again get a 50-50 split. At this point, you might be confused, because now we've indicated that it's possible for Alice and Bob to find both of their particles to be spin up or spin down. But again, remember that they're measuring spin in different directions. Alice is measuring the component to spin in the x direction of her particle, and Bob is measuring the spin in the z component of his particle. And all we know is that their spins in the x direction have to cancel out, and their spins in the z directions have to cancel out. But if they're each measuring spin in different directions, those don't have to cancel out. They're just two components of a vector that neither knows the whole of. Again, just because Alice measures that her particle is spin up in the x direction, it doesn't mean it doesn't have spin in the z direction. It means its spin in the z direction is not well defined. Or alternatively, if the spin in the x direction is well defined, if there's no uncertainty about the spin in the x direction, it means there is uncertainty about the spin in the z direction. And likewise for Bob. Bob is measuring spin in the z direction, not spin in the x direction. And so the fact that they're both spin up, they're not the same spin up. They're spin up in different directions. There is another possibility. Alice could be sneaky and choose not to make any measurement at all. And if Alice makes no measurement at all, then Bob is fed the initial superposition state of the system, in which case Bob's measurement collapses the superposition with a 50% chance of finding spin up in the z direction and a 50% chance of finding spin down in the z direction. Now, of course, again, there are other possibilities as well. Alice could make a measurement in the y direction or something in between. But the point of this is that no matter what, to Bob, it looks completely random. If Alice performs measurements in the z direction, in this particular reference frame, it's true that that determines the outcome of Bob's experiment. If Alice measures spin in the z direction and gets spin up, then Bob will get spin down. And Alice knows this. And if Alice measures spin down, then Bob will get spin up. However, Alice has a 50% chance of each of these happening. And so in each particular experiment, there is a 50% chance that Bob will get spin down or spin up because it corresponds opposite to whatever Alice got. So from Bob's perspective, he can't tell. And if Alice measures spin in the x direction, then Bob actually has an actual probabilistic chance. Alice cannot predict what Bob will get any more than Bob can. They will both know, or they'll both think, that he has a 50 chance of either one, whether Alice gets spin up or spin down in the x direction. And if Alice performs no measurement, then Alice likewise can't make any predictions about what Bob will find, and neither can Bob, other than, again, that it will be random. So even if we enable our two participants in this experiment to perform measurements of spin in different directions, there's still no room for communication between them this way. For example, we could say Alice might tell Bob, listen, sometime I'm going to measure the spin in the z direction, and other times I'm going to measure spin in the x direction. When I measure spin in the z direction, I mean a 1, and when I measure spin in the x direction, I mean a 0. If Bob could figure out which direction Alice performed her measurement, he could use this, or they could use this to send information from Alice to Bob, because a string of 1s and 0s is just how we transfer data right now. But Bob can't do that. Bob can't tell what Alice did, because on his end, the results are indistinguishable. And so there is no way to use quantum entanglement to communicate from one place to another. And this is how, even though the effects of entanglement are instant across vast, arbitrarily large distances, it doesn't violate special relativity because there is no information being transported from one place to another at a rate greater than the speed of light. There is still the problem of simultaneity, right? We established that in different reference frames, the order in which Alice and Bob performed their experiments is different. And so who caused the collapse? Did Alice's measurement collapse the wave function determining the state of the positron, which Bob then measured? Or did Bob measure the state of the system, collapsing the state of the electron, which Alice then measured? The answer is yes. This is just one more thing for people to disagree about in special relativity. Now, in the past, we've always said, yeah, so you can't disagree about what happens, right? We can disagree about when things happen. Sometimes we can disagree about the order in which they happen. We can disagree about where they happen, how fast they're happening. But there are some things we can't disagree about. A train going through a tunnel gets chopped in half or it doesn't get chopped in half, and so on. And so this seems a little bit in violation of that, but it's really not. Because remember that the effect of wave function collapse in this context is not detectable. What happens is that Alice measures spin up and Bob measures spin down. And that happens in each of these reference frames. It just happens for different reasons in each of these reference frames. And so if you could wrap your head around the fact that Alice and Bob can disagree about how old each other are, as long as they remain in their own separate reference frames, it shouldn't really be any harder to accept that they can also disagree about who caused the collapse of the wave function. Because in the end, when they compare their notes, they will find that their spins are always in the opposite direction, and that is the event that they cannot disagree about. The outcome of their measurement is the measurable event in question. And those are consistent in either circumstance. The same thing does happen in each reference frame, but for different reasons, just like we often found in special relativity. If this hasn't made your brain hurt, you should probably go back and rewatch this video and maybe the previous one, because you're not getting it. If your brain is hurting, that's probably a good sign. One thing I'd like to point out is that in the beginning of the year when learning special relativity, I think all of you felt pretty uncomfortable about a lot of the concepts and the realities that you were forced to accept about a relativistic universe. So something that used to make you uncomfortable, maybe even still does a little bit, is now the bedrock that, when sort of challenged a little bit, makes you uncomfortable. See how far you've come. This is one of the things that I love about physics. At every level, it forces you to challenge your preconceptions. When you all were learning physics for the first time last year, or whenever your first time learning physics was, you all, I think at some point, had to deal with misconceptions that you built up through your life, through your experiences, that when faced with better data or when forced to think about it more clearly, you realize that the way you thought things were was not actually the way things are. That has happened, I think, on a much greater scale this year, and it never really stops. That's what physics really is. It's about understanding the nature of the universe, understanding how it is, or at least learning how we can best model it, based off of data in as objective a way as we know how to do. And sometimes that means coming to terms with the fact that the things that we believed were obviously true are not so true at all. And I think that's a generalizable skill. If you can get used to the fact that our beliefs, even if they're based in experience, are not always true, and if you can force yourself to consider new information about anything in any walk of life, and if you're willing to revise your beliefs based off that information, it helps you go through life with a more open mind and with a healthy dose of skepticism. I think that's a good thing.